as well as stress and strain. And I believe you guys have learned it during the lecture, but here's a brief review of the equation that we're going to use for today's lab. So first, how do we calculate the stress? If you look at the equation, it's the force divided by cross-sectional area. So when you apply force to the object, use a force and divide by the cross-sectional area. That'll be the stress. And also, when you apply the force to the object, probably the object will have a dimensional change. Usually it's a change at the lanes. So how do we calculate strain? We use the elongation divided by the original length. So take this object for example. When we apply force to it, the change of length is delta L here. So we use delta L divided by L0, which is the original length. That'll give you a strain. So here, these two equations are pretty important for today's lab, and you're going to use them a lot of times. And we can talk about stress first. Why do we use the force divided by cross-sectional area? What does that mean? Here's a simple example. So say this muscle can afford maximum 10 newtons, and it has a cross-sectional area of 10 centimeters square. So how do we calculate stress in this case? We use 10 newtons divided by cross-sectional area, which is also 10. So for stress, you got 10 over 10 equals to 1. And say, in this case, we put two muscles together in parallel, or we can consider it as a bigger muscle. And this muscle can afford 10 newtons for each fiber, so it can totally afford 20 newtons. And the cross-sectional area is double, so it's now 20 centimeters square. How do we calculate stress in this case? We use total force divided by total cross-sectional area, which will be 20 over 20 equals to 1. So you can see, wow, even though the muscle size is pretty different, the stress when you calculate is the same. That means actually we're ignoring the size of the object and we're only focusing on material. So if it's muscle fiber, we don't care if it's 2 or 3 or 5. We don't care if it's a big muscle or small muscle. If the material is the same, we expect to get the same stress when we apply force to it. So we know that muscle consists of multiple muscle fibers, and when we apply a force to it, we want to know the force like distributed to each unit. That's the idea of stress. We divide the force by its cross-section area, so we know how much force is applied on each unit. So that means that we're ignoring the size of the muscle and we're only focusing on the material. Okay, and after stress, we want to know what's the difference in why do we calculate strain in this way? So it's pretty similar example. We have a muscle fiber and the original length when it's at rest, it's 10 centimeters. So we calculate the strain, which is delta L is 0. There is no change in the length, right? And the original length is 10. So 0 divided by 10 equals to 0. And then we apply 10 Newton force to this muscle fiber. And it extended a little bit. So the change of length would be 2 centimeters, right? Because it's originally 10 centimeter. And we apply force to it. It extended for 2 centimeters. So delta L is 2 divided by original length, which is 10. So we got 0.2. Then we put two muscle fibers in series, or we can consider it as a longer muscle. And we apply the same force to it, each muscle fiber will extend in the same amount. So 12 and 12. Totally elongated 4 centimeters. And divide by original length is 20 because we put two muscle fibers together, right? And 4 divided by 20 equals to 0.2, which is the same when it's in single muscle fiber or two muscle fibers in series. You got the same strain. So that's the same idea that we just want to know how much does one muscle fiber elongated. That means we only concerned about the material. We want to know about the elongation of each unit, and we're ignoring the length. So if it's a short muscle or if it's a long muscle, it doesn't matter. When you calculate the strain, it'll probably only related to the material. Okay, so when we put stress over strain in a ratio, that's Young's modulus. That's a super important idea for today's lab. So basically, we're going to calculate stress and strain and then put them together to get a Young's modulus. And we know stress is more related to the material, and also the strain is in the same idea. So we divide it into one unit of a certain material. That means for Young's modulus, actually, each material has its own number. So say muscle fibers is here. Doesn't matter if it's a long or a short muscle or a big or a small muscle. Usually you got the pretty similar Young's modulus. So that's the first idea. We want to know the force applied and the elongation for each unit. So that's only related to the material. We divide into each unit. So it's more a material property related index. That's why each material has its own Young's modulus. Doesn't matter if it's a big one or a small one, a long one or a short one. The second idea is that the strain can be elastic or it can be plastic. What does that mean? Think about when you stretch your Achilles tendon. Usually in daily life, it's an elastic uh, situation. When you elongated it, it'll come back when you release the force. But when you apply more and more and more force to it, it'll finally come to a yield point. That means it comes to plastic situation. It's a permanent change of the length or the material. That means your probably say ACL. Usually we want it to be in elastic condition, but when the force is too much, you go to yield point. Sometimes you got like pretty loose ligaments that make your knee a little bit shaky. And then when it comes to ultimate strength, it'll finally failure. That means you get like ACL rupture or Achilles tendon rupture. That's where the sports injury happens. So when we look at elastic portion, we use the stress divided by strain, which is the slope for this line. You can see the slope is pretty consistent from here to here. In the elastic portion, the Young's modulus is a constant number. Okay, so think about it. Say we have two materials, one is stiffer, the other is more flexible. Which one will get a higher E, means higher Young's modulus? Think about it. When we apply the same force or same stress to it, the stiff material will elongate with shorter strain, right? It won't change that much of the length. So the denominator will be smaller. That finally causes higher E. So the stiffer material will have higher E, and the more flexible material will have lower E. Okay, then how do we calculate E into today's setting? Today we're going to calculate the Young's modulus for a spring, and for a spring in different situation. We'll talk about it later in next slide. But how do we calculate Young's modulus for, say, this small short spring? We're going to apply a force to it. So you can see the force at the scale here. We're going to pull the spring. So you use the force saw on the scale, divide by the cross-sectional area. You get stress. And also, we use the delta L, which is a change in the length, divide by original length. You can get strain, right? Remember the two equations. Okay, so that's how we calculate Young's modulus in today's setting. Here's the table for today. So we're going to apply force with 0 pounds, 2 pounds, 4 pounds, 6 pounds, and 8 pounds, 10 pounds. And then you're going to get a certain length at when certain force is applied to it. And then we'll get, I'm going to calculate this cross-section area for you. So you use force divided by cross-section area. You'll get a stress, and put in this column. How do we calculate cross-section area? Remember this equation, pi r squared. R is the radius of this circle. So for exercise 1, 2, 3, we're calculating the cross-section area for a spring, which is a circle. So I'll measure the radius for the spring, and then I'll square the radius and times pi. You'll get cross-section area. And for exercise 4 and 5, the cross-section area is here. So for a bungee cord in exercise 4, it's 0.04 pi. And for a rubber band in exercise 5, it's a rectangle shape, so there's no pi here. It's 1 centimeter square for rubber band. And don't worry about these numbers. You'll see those in the table. I'll post it in the module. Okay, so here is today's setting. The first exercise, we have a spring, and we're going to apply a certain force on it. So you can calculate stress and strain for a single spring. And then for exercise 2, we're going to put a spring in parallel, which simulate a bigger muscle. So the cross-section area will be doubled, and we're going to apply certain force on it, which is from 0 to 10 newtons. And then, the force will be in newtons. So this slide is a little bit wrong. It's wrong. Yeah, I'm going to change it to newtons. Sorry about that. So for exercise 2, we're going to put 2 springs in parallel and also apply the same force to see the length of change. And then for exercise 3, we're going to put 2 springs in series that simulates a longer muscle. And we're going to apply force on it and see the stress and strain for that. And because stress and strain is mostly related to material, so we expect the Young's modulus will be pretty similar between these 3 exercises. And for each exercise, we have 2 kinds of spring. So we've got a short spring and a long spring. I'll show you the spring. How does it look like in the next slide? And so yeah, we got short spring and long spring. For exercise 4, we got a bungee cord. Exercise 5, you got a rubber band. And here's everything we need for today's lab. So you can see here is a short spring in parallel, which is exercise 2, and in series, which is exercise 3. And also a long spring in exercise 1 in single, parallel in exercise 2, series in exercise 3. So here's 1, 2, and 3. And this one is a bungee cord for exercise 4. And this is a rubber band for exercise 5. Okay, that's for today's lab. And for the assignment, there will be 3 graphs. So yeah, you can use Excel or just draw it by your hands. Both are fine for me. And you don't need to include all the tables. I'll post it for you. And there are 6 questions. You need to answer all of them. So I'll see you later in the data collection clip. And if you have any suggestions, please don't hesitate to shoot me an email or schedule a meeting with me. I'll see you guys later.